Good morning. Today we are going to learn a new type of discrete random variable, which is called hypergeometric distribution. So after today's lesson, you will be able to calculate and interpret hypergeometric distribution, solve real-world problems involving hypergeometric distributions, review Unit 2A, and be prepared to take Unit 2A assignment. Okay, first, let's look at hypergeometric distribution. So as before, first, we're going to learn what is hypergeometric distribution. That includes probability distribution, mean, and standard deviation. And after that, we'll have a look at the applications of hypergeometric distribution. Okay, first, intuitive way to understand a model. Okay, first, suppose we have n elements. Okay, I'll draw a diagram here. Okay, we have a uppercase n elements in total in this container, of which there are r successes. Okay, of which there are r successes. That means there are n minus r failures, right? And then we pick lowercase n elements from the uppercase n total elements without replacement. Okay, we pick lowercase n from this container. So as you can see here, there should be some successes in the n and some failure in the n, right? So the number of successful elements in our lower n number of elements is a random variable. So let x be the number of successes of the lowercase n elements we pick. Okay, we denote the successful elements here as uppercase x. Then x is a random variable, right? Because the value of x varies. Then x is a random variable and x yields to a hypergeometric distribution, denoting as x yields to a hypergeometric distribution, which have three parameters. The first parameter, lowercase n, is the number of elements you pick from the container. The second parameter, uppercase n, is the total number of elements in the container. The third parameter, r, is the number of successful elements in the container. So the next question is, do we have any formula that can be used to calculate the probability distribution of x? That means for any given value k, is there a formula to calculate the probability of x being k? Okay. To calculate the probability of x being k, we can use this formula, which we have learned in Unit 1, right? The probability of event A is the number of sample points in event A divided by the number of sample points in the sample space, right? Okay, here, what is the sample space? Sample space is actually picking lowercase n from the uppercase n different elements, right? This is your total number of sample points in the sample space. So how about the number of sample points in this event? Okay, to complete this event, there are two steps. Okay, the first step is to pick k successes from the r successes, right? And the second step is to pick lowercase n minus k elements from the remaining uppercase n minus r elements, right? So this is the probability of x being k. It should be noted that r here should be equal to or less than uppercase n, and lowercase n equals to or less than uppercase n. Of course, here k should be 0, 1, 2, etc. until the minimum value of n or r, right? The maximum value of k depends on the values of n and r. It should be the minimum value of n or r, right? Otherwise, for other value of k, the probability is 0. So this is our probability distribution for a hypergeometric distribution. Any questions? Okay, let's summarize. So here, suppose we have n elements, of which there are r successes. Of course, r is equal to or less than the uppercase n, right? Meaning there are uppercase n minus r failures. Then we pick lowercase n elements from the uppercase n total elements without replacement. Let x be the number of successes of the lowercase n elements we pick. Then x is a random variable, and x yields to a hypergeometric distribution, denoted as x yields to a hypergeometric distribution. First parameter, lowercase n, is the number of elements you pick from the container. The second parameter, uppercase n, is the total number of elements in this container. The third parameter, r, is the number of successful elements in the container. So the probability of x being any value k for k being 1, 0, 1, 2, and minimum of r n is given by this formula. It's a ratio. For other values of k, this probability is 0. Okay, any questions? Okay, for the mean, okay, if x yields to hypergeometric distribution, then the mean of x, or the expectation of x, is given by this formula. It's also a ratio, which is lowercase n times r divided by uppercase n. Please write this in your journal. And there is no shortcut to calculate the variance. If you want to calculate the variance, you have to use the definition or the second formula derived from the definition, which is the expected value of x twice minus the expected value of x to the twice. Right? Any questions? No? All right, let's see an example. From manufacturing mixed auto parts that are sold to auto dealers. Last week, the company shipped 25 auto parts to a dealer. Later, it found out that 5 of those parts were defective. By the time the company manager contacted the dealer, 4 auto parts from that shipment had already been sold. What is the probability that 3 of these 4 parts were good parts and 1 was defective? Okay. What does this mean? What's the random variable here? You selected 4 auto parts, right? The number of defective ones is a random variable. So that means basically you can draw a diagram to illustrate this. Okay. In total, there are 25 auto parts, right? And of these 25 auto parts, there are 5 defective ones. So the successful elements are here is 5. That means we have 5 defective parts. And then we select 4 auto parts. That means lowercase n here is 4, right? Select 4 auto parts from the container, and we denote the number of defective ones as x. So here it asks you to find the probability of x being 3. Oh, sorry, being 1, right? Because as here, 1 was defective. According to hypergeometric formula, this probability is actually a ratio. Okay, let's see how we can achieve this. Okay, the first term is to choose 1 defective ones from the 5. The second number would be to choose 3 good ones from the 20 good ones, right? And in the sample space, number of sample points are to choose 4 elements from the 25, right? Okay. So here we can calculate this. Which is 5 factorial, 1 factorial by 20 factorial, 3 factorial, 20 minus 3 factorial, divided by 25 factorial, divided by 4 factorial, 25 minus 4 factorial, which is 0.4506. Okay, any questions? No? All right, let's see the next example. Dawn Corporation has 12 employees who hold managerial positions. Of them, 7 are female and 5 are male. The company is planning to send 3 of these 12 managers to a conference. If 3 managers are randomly chosen out of 12, A, find the probability that all 3 of them are female. B, find the probability that at most one of them is female. Okay, I'll leave these questions for you to solve. I'll give you 10 minutes, okay? At the meantime, okay, let's solve this first. Okay, let's have a look at this together. Okay, so basically here you have 12 employees, right? Okay, suppose we have a container that there are 12 employees. So the uppercase N is 12 employees. Of them, 7 are female and 5 are male. Okay, so there are 7 female. All right, okay. So here's the number of successful elements, 7. And the company is planning to send 3 of these 12 managers. So we pick 3 out of the 12, right? So here, lowercase n is 3. And we denote the number of female managers as x. Then according to hypergeometric distribution, x, the random variable x here, yields to a hypergeometric distribution, right? Okay, x yields to a hypergeometric distribution. First parameter, lowercase n, is 3. Second parameter, uppercase n, is 12. The third parameter, r, is 7. Okay. First question, find the probability that all 3 of them are female. That means find the probability of x being 3, right? Which is a ratio of number of sample points in this event. That means, first of all, we choose 3 female from the 7, right? And the second step is to choose the remaining 0 from the remaining 12 minus 7. The total number of sample points in the sample space to choose 3 from the 12, right? Okay. So after calculation, this probability is 35 over 220, which is 0.1591. Okay, any questions? No? All right, let's have a look at B. Find the probability that at most one of them is female. At most one of them means x equal to 1 or less than 1, right? Which is the probability of x being 1 plus the probability of x being 0, right? Okay, for the probability of x being 1, it is a ratio between the sample space in this event, the sample points in this event, which is choose 1 woman from the 7, and then choose the remaining 2 from the remaining 5. The sample space does not change, which is also choose 3 from the 12. Okay. This ratio plus the probability of x being 0, which is also a ratio, which is to choose 0 woman from 7, and then to choose 3 from the remaining persons, divided by the number of sample points in the sample space, okay, which is 0.3182 plus 0.4 0.0455. Okay, so the sum of them is 0.3637. So this is a probability you are looking for. Okay, have a look at this. Do you have any questions? No? All right, so basically this is a hypergeometric distribution. Next, let's do a quick review of Unit 2A, which is the first half of Unit 2. Because tomorrow we'll do an in-class assignment. So we'll do a quick review here and then do some exercises and prepare for the next assignment, okay? Okay. So in the first half of Unit 2, what we have learned is the first aspect is to know what is a random variable, right? And also, what are the types of random variable? Okay, there are two types of random variable. The first type is discrete array. The second type is continuous array. Okay, for continuous array, if in the number axis, if there exists at least one interval that this random variable can be any value within this interval, then it is a continuous array, right? Otherwise, it is discrete array. For discrete arrays, values are discrete and countable, right? There does not exist any interval in which the random variable can be any value. You have to be able to differentiate these two types of random variable. Okay. All right. Next, we have learned some properties of the discrete random variable description or the description of discrete random variable, which includes first how to describe the probability distribution of a random variable. Probability distribution of DRV. DRV means discrete random variable. Okay, so probability distribution is usually described by a table, right? The first row are the value, all the possible values that X can assume, such as K1, K2, etc., Kn. The second value denote the corresponding probability, X being K, such as P1, P2, and Pn. And we can also describe this probability distribution using a bar chart, right? Its x-axis is values that x can assume. The y-axis is responding probability. Okay, you can also use a bar chart to illustrate the probability distribution. For example, this is a bar chart illustrating the probability distribution of x, right? Okay, next, we discussed the expected values or expectation or mean. Expected values. Expected value, or sometimes we call it expectation or mean. Okay. Of discrete random variable. Okay, for a discrete random variable, the expected value of x is actually a sum, right? Sum of each value times the corresponding probability of being this value for all n, for all x, for all values, right? And we denote the expected values as sigma. And also, for any given discrete random variable x, if there is a function called fx, then fx is also a random variable, right? If you know how to calculate the mean of x, you will also know how to calculate the expected value of fx, right? The expected value of fx is also a sum of all values of the function times the probability of x being each value. That means you have to be able to calculate any given function on the random variable. Understand? Of course, there are some formulas for you to use to simplify your calculation, such as the expected value of ax plus b is, you can calculate the expected value x first, and then times a plus b, right? And other properties include the expected value of any constant is itself, right? And the expected value of two functions is the expected value of function 1 plus the expected value of function 2, something like that. Okay. Next, we discussed how to calculate the variance. Okay. Variance, VAR of a discrete random variable x is defined as x minus ex to the square e. Right? This is a definition of variance. But usually in practice, we use the second formula derived from the definition, which is the expected value of x to the twice minus the expected value of x as a whole to the twice, right? Okay, we use sigma to the twice to denote the variance. Okay, so after that, we learn how to calculate the standard deviation of a discrete random variable. Standard deviation SD of x, which is denoted by sigma, is defined by the positive square root of the variance of x. Right? Okay, in a summary, the expected value of x describes the overall level of x, how large or how small x is. The variance describes the level of dispersion of x. So how large or how small is the dispersion, right? Okay. Next, we discussed some of the specific discrete random variable. Okay. Number 3, some specific discrete random variable. Okay, the first discrete random variable we learned is called discrete uniform. Distribution. Okay, for discrete uniform distribution, suppose x can be the values of x1, x2, and xn. The probability of x being each value xi are all the same, right? Which are all 1 over n, 1 over n, and 1 over n, right? And there is a shortcut to calculate the expected value for a discrete uniform distribution. Which is Ex equals to 1 over n and the sum of xi. Okay, for VARX, there is no shortcut. We still use the derived formula to calculate the variance and the standard deviation. Okay. The second distribution we learned is called binomial distribution. To qualify for a binomial distribution, remember there are 4 conditions to be fulfilled, right? 4 conditions. Pay attention to these 4 conditions. Only these 4 conditions fulfilled, it is a binomial distribution. Okay, if x yields to a binomial distribution with two parameters n and p. N is the total number of experiments. P is the probability of being successful in each experiment and in each trial. Then the probability distribution of x is given by this formula. For any value k, the probability of x being k is given by Cnk. P is the case. 1 minus p to n minus k for all k equals to 0, 1, 2, until n. For any other values, this probability is 0 because x cannot be any value except from 0, 1, 2, 3 until n, right? So this is the probability distribution. You can also calculate these values and list them in the table, right? You can use a table, use a formula, or use a bar chart. There are three ways to illustrate the probability distribution. And for expected values of x, this value can be calculated by n times p. For variance of x equals to n times p times q, where q is 1 minus p. Understand? Any questions? Of course, binomial distribution is a key point in this unit. Pay attention to this distribution. There are a lot of applications that involves binomial distribution. All right? Okay. And at the end of this unit, and at the end of the first half of this unit, we learned hypergeometric distribution. In today's lesson, we learned hypergeometric distribution. Also, for hypergeometric distribution, it must fulfill some conditions, right? Suppose we have a container, there are n distinct elements. Of these n elements, there are successful elements. And then we pick lowercase n from this container, right? And then we denote the number of successes as x. Here, x yields to a hypergeometric distribution. There are three parameters, which are lowercase n, uppercase n, and r. The meaning of, you should be clear with the meaning of lowercase n, uppercase n, and r, right? Lowercase n is the number of items you pick from the container. Uppercase n is the total number of elements in the container. And r is the total number of successes in this container. If x yields to a hypergeometric with these three parameters, the probability of x being any value k is given by a formula, right? Depends on the k. For k equals to 1, 2, 0, 1, 2, 3, until the minimum value of n and r. Formula is a ratio between the total number of sample points in this event, which is CRK times C uppercase N minus R lowercase n minus k over C uppercase N lowercase n. For any other values, this probability is 0 because x cannot be any other values, right? Okay. And the expected value of x is given by lowercase n times r over uppercase n. This is the expected value of x if x yields to a hypergeometric distribution. As to VARX, there is no shortcut to calculate this. So we'll use the derived formula, which is EX squared minus EX as a whole to square. Understand? Okay. So this is a quick review of Unit 2A. Okay, if you have no questions, let's take a 10 minutes break. Please return in 10 minutes and we'll do some exercises. Okay, welcome back. And then let's do some practices on Unit 2A to prepare for the next assignment. All right. Okay, let's see the first question. An 8-sided die has its faces numbered 2, 4, 6, and 16. What is the expected outcome on a typical row? Okay, I'll give you 2 minutes to finish this. Okay, finished? So here it asks you to calculate the expected outcome, right? Expected outcome. Apparently, this is a discrete uniform distribution. So the expected outcome here is, because 8-sided. So this is the expected value of x if x is a discrete uniform, right? So n here is the total number of sample points. So here we have an 8-sided die, so n is 1/8, and times 2, 4, plus 6, and plus 16, which is times 8 divided by 2, which is 9. So the correct answer here is C. Okay, any questions? No? All right, let's see the next one. The binomial and hypergeometric distributions are similar in that. Okay, choose the correct answer here. All right, have you finished? Okay, let's see this in detail. The binomial and the hypergeometric distributions are similar in that A, they both use independent trials. This is incorrect because for hypergeometric distribution, the trials are not independent, right? Because this is a sampling without replacement process. So each time when the choice in the previous step does have impact on our choice in the next trial. So all trials are not independent. Okay, B, they both use dependent trials. Again, this is not correct because for binomial distribution, all the trials are dependent, but for hypergeometric distribution, the trials are not independent. So for binomial distribution, the trials are independent. So B says they both use dependent trials. This is not correct. C, they use the same formula for calculating expectation. This is incorrect because apparently they use different formulas to calculate the expectation. D, they both involve counting successes. This is correct. In binomial distribution, we count the number of successes when we conducted n different trials, right? For hypergeometric distribution, the intuitive model is in the container there are uppercase n elements of which there are successful elements. So it also involves counting successes, right? So the correct answer here is D. Okay, any questions? No. Let's see the next one. The expectation for a uniform distribution is calculated using A, B, C, or D. Okay, this is a simple one. Let's have a look at this. The expectation for a uniform distribution apparently is calculated using A, right? This is a formula we use to calculate the expected value for a uniform distribution. Okay, next, counting the number of tails when a coin is flipped 20 times is an example of A, B, C, or D. Okay, so here, the coin is flipped 20 times means we conducted 20 times of experiment, right? There are 20 trials, and each trial should be independent with each other, right? Because what you have flipped does not have impact on the next flip. And in each trial, the probability of being a tail is constant. So according to the four conditions, it fulfills all the conditions of binomial distribution. So it is a binomial distribution. Any questions? No? All right, let's see the next one. The probability that exactly 2 students will be selected when 5 people are selected from 4 students and 3 teachers is A, B, C, or D? Okay, let's have a look at this. Okay, this question tells you that in total you have 4 students and 3 teachers. And the task is to choose 2 students. Sorry, the task is to choose 5 people, right? Of these 5 people, there are 2 students. So it asks you to calculate the probability that exactly 2 students will be selected out of the 5 people. Okay, apparently here, in this container, there are 7 people in total. And the number of students is R, which is 3, right? And lowercase n, that is the number of elements you draw from the container, which is 5. And the number of students we denoted as x. And x here goes to a hypergeometric distribution. 3 parameters are 5, 7, and 3. So here we calculate the probability of x being 2, which is a ratio between the number of sample points in this event, which is to choose 2 students from the 4, and then to choose 3 teachers from the 3, and divided by the number of sample points in the sample space, which is to choose 5 people from the 7 people. So the correct answer is B. All right, any questions? No? Okay, let's see the next one. A particular traffic light is programmed to be red 40% of the time on his day Monday to Friday commute to and from work. What is the expected number of times Jack can expect to have a red light? Okay, I'll give you 5 minutes to solve this question. All right, did you finish? Okay, in this question, Jack passes this traffic light 10 times, right? Because Monday to Friday there are 5 days. On 5 days, there are two trips, right? Commute to and from work means 2 trips per day, and there are 5 days. So in a week, he passes this traffic light 10 times. And each time is actually a trial, right? Each time he passes traffic light, he checks the color of the traffic light. So there are 10 trials. Each trial is independent with each other. And in each trial, the probability of seeing a red light remains constant because it says the traffic light is programmed to be red 40% of the time, right? So this is a binomial binomial experiment. Okay, what is random variable here? Okay, first of all, let's use uppercase X to denote the random variable here. Let X denote the number of times Jack sees a red light in the 10 trials. Then X here yields to a binomial distribution. Okay, N is 10, P is 0.4, right? And here this question asks you to calculate the expected number of times Jack can expect to have a red light. So it asks you to find the expected value of X, which is according to binomial formula is NP, which is 10 times 0.4, which is 4 times, right? So here, the expected number of times Jack can expect to have a red light is 4. Okay, any questions? All right, let's see the next one. The beaver population in the particular provincial park is known to be 452. 200 beavers were caught and tagged. If 65 beavers were later caught and checked for tags, how many would you expect to be tagged? Okay, I'll give you 2 minutes to complete this task. All right, let's have a look at this. So here's the total number of beaver is 452, right? Okay, usually we use uppercase N to denote total number of elements. And 200 beavers were caught and tagged. So the number of successes are 200. Okay. Imagine there's a container that contains these elements. And later we caught 65 beavers. That means we pick 65 out of the 452. And we denote the number of beavers with tags as x. So x here is yielding to a hypergeometric distribution, which has the following three parameters. Right? And it asks you to find the expected number of x. So according to the formula, if x yields to a hypergeometric distribution, the expected value of x is n times r divided by uppercase N, which is 65 times 200 divided by 452. Okay, so the final result is approximately 28.76. Okay, any questions? No? All right, let's see the next one. Okay. A certain cell phone provider's helpline is busy 95% of the time. In 15 calls to the helpline, what is the probability that it will be busy every time? At least 12 times. What is the expected number of times a caller should expect the line to be busy in 15 attempts? Okay, I'll leave you 3 minutes to finish this question. All right, have you finished? Okay, let's look at this problem together. To finish a problem like this, first of all, we need to know what is a random variable here, right? So in the 15 calls, the number of busy times is a random variable. It could be any value between 0 and 15, right? So here we use uppercase X to denote the random variable. In the 15 calls. Then apparently, according to our analysis, X yields to a binomial distribution. The first parameter is 15 calls. The second parameter is the probability of being busy, which is 0.95. So in question A, it asks you to calculate X being the probability of X being 15, right? According to the binomial formula, the probability of X being 15 is C 15, 15, 0.95 to 15 times, and 0.05 to 0 times, which is approximately 0.4633. Okay, B. At least 12 times means the probability of X being 12 or above 12, which is X being 12, the probability of X being 12 plus the probability of X being 13 plus the probability of X being 14 plus the probability of X being 15. Okay, I'm not gonna calculate this for you here. Please try to solve this after the class, all right? B, what is the expected number of times a caller should expect the line to be busy in 15 attempts? That means you have to calculate the expected value of X, which is NP, which is 15 times 0.95. And this number should be 15 by 0.95. Which is 14.25. Right? Any questions? No? Okay, let's see the next one. 18 of 30 players selected in NHL first round draft were Canadian. If 7 drafted players are randomly selected, what is the probability that A, only 1 is Canadian, B, all are Canadian, C, most of them are Canadian? Okay, I'll give you 5 minutes to finish this question. All right, have you finished? Okay, first of all, again, let's see what is a random variable here. So here we have a collection of 30 players, right? You use an uppercase N to denote the 30 players, of which there are 13 Canadians. Oh, sorry. Okay, yes, there are 18 Canadians here. And the task is to select 7 players. That means lowercase n is 7, right? Of course, in the 7 players, there could be Canadians. There could be some Canadians, right? We denote the number of Canadians as X. So here, let X denote the number of Canadians in the selected 7 players. Then apparently here X yields to a hypergeometric distribution. The 3 parameters are 7, 30, and 18, right? Okay, so question A, only one is Canadian. The probability of only one Canadian, that means probability of X being 1 is given by a ratio, which is right? Okay, again, I'm not going to calculate this. You are going to calculate this after the class. B, all are Canadians means probability of X being 7. Okay, is given by a ratio, which is choose 7 from 18 Canadians and choose 0 from the rest of the people, divided by choose 7 from the 30 players. You see, most of them are Canadians. What does this mean? Most of them are Canadians is equivalent to X equal to 4 or more than 4, right? So this is the probability you are looking for, in which you have to calculate the probability of X being 4 and the probability of X being 5 and the probability of X being 6 and the probability of X being 7 using the hypergeometric formula we have learned, right? Okay, I'm not gonna calculate this. Please do calculate it by yourself after the class. Any questions? Okay, if you do not have any question, let's see the next one. It is known that the screws produced by a certain company will be defective with a probability of 0.01 independently of each other. Company sells the screws in a package of 10 and offers a money-back guarantee that at most one of the 10 screws is defective. What proportion of packages sold must be the company replaced? Okay, I'll give you 5 minutes to solve this question, and then we'll have a look together. All right, have you finished? What's the random variable here? Okay, first of all, let's use the uppercase X to denote the random variable here. Let X denote the number of defective screws in the package. Then here X yields to a binomial distribution, right? First parameter is 10 because we have 10 screws in a package. That means there are 10 trials, right? For each screw, the probability of it being defective is 0.01. So here the question asks you to calculate the proportion of packages sold the company must replace. That means you are going to calculate the probability of X being above 1, right? Because if the number of defective screws is more than 1, you have to replace this package to your customer, right? So the probability of X being above 1 means the probability that the packages sold the company must replace. Okay, here if X is more than 1, that means X could be 2, 3, 4, 5, 6, 7 until 10, right? So it is easier for us to calculate the opposite of it, which is 1 minus the probability of X equal to or less than 1, which is 1 minus the probability of X being 0 plus the probability of X being 1, right? Okay. Probability of X being 0 according to the binomial formula is C10 0, 0.01 to 0 times 0.99 to 10 times minus C10 1, 0.01 to 1 time and 0.99 to 10 times. Okay, the final result is approximately 0.004. Okay, so 0.4% of the packages will have to be replaced. Okay, any questions? No? Okay, let's see the last question. A communication system consists of n components, each of which will independently function with a probability p. The total system will be able to operate effectively if at least one half of its components function. For what values of p is a 5-component system more likely to operate effectively than a 3-component system? Okay, this question asks you to calculate the value of p such that a 5-component system more likely to operate effectively than a 3-component system. Okay, I'll give you 5 minutes to solve this question. All right, let's see how we can solve this question. Okay, so what's the first question we should ask is what's the random variable here? Okay, actually the number of functioning components is a random variable, right? So first let x denote the number of functioning components. Then apparently x yields to binomial distribution. First parameter is n, right? N is the total number of components. B is the probability that the component will function correctly. So this question asks you to decide a proper value of P such that a 5-component system more likely to operate effectively than a 3-component system. So here we first will calculate the probability of 5-component system can operate effectively is Px equals to or more than 3, right? Because it says in order to operate effectively, at least 1/2 of its components should function, right? The half of 5 is 3. So there are at least 3 components function properly to make the 5-component system operate effectively. That means the probability of x being 3 plus the probability of x being 4 plus the probability of x being 5, which is C5 P2 3 times 1 minus P2 twice plus C5 4 P to the 4th 1 minus P2 once plus C5 P2 5 times 1 minus P2 0 times, which is C5 P3 1 minus P2 twice plus C5 P4 1 minus P plus P5, right? Okay. And then we should calculate the probability of 3-component system can operate effectively. Okay, the half of 3 is 2. So x should be equal to 2 or more than 2. That means x could be 2 or x could be 3, right? Okay, which is C3 2 P2 1 minus P1 plus C3 P3 1 minus P0, which is 3 P2 1 minus P plus P3, right? Okay. And in order to make the 5-component system is better, the 5-component system is better, we need to make the first probability more than the second probability, right? That means we have to make this probability, which we have calculated above, more than the second probability. Okay, in order to make this happen, we need to simplify by factoring, right? Okay, if we factor and cancel some terms, we can have 3p minus 1 twice times 2p minus 1 more than 0, right? In order to achieve this, apparently p minus 1 square is above 0 and 3 is above 0. So we need to make 2p minus 1 more than 0. That means we need to make p more than 1/2, right? So this is our final result. When p is more than 1/2, the 5-component system is more likely to operate effectively than a 3-component system. Okay, any questions? Okay, if you have no questions, this is the knowledge and practices in today's class.